Hi everyone, this is your video from Mrs. Shiwi on lesson 6.1 in college algebra. Topic for this lesson is higher degree polynomial functions. We're going to look at cubics and quartics and talk about their max and their min and their behavior. So first off, we're going to talk about cubic functions. Well, what is a cubic function? It has to have an x to the cube to the third term. X squared plus cx plus d, those may or may not exist depending on the values of b, c, and d, but there has to be an x cubed and nothing higher degree than that or it's not a cubic. The end behavior is going to be one end is going up and the other end is going down. We talked about that earlier when we talked about polynomials. Odd functions have one end up, one end down, and even functions have both ends up or both ends down. That is part of this lesson a little bit later on. The other thing that this has is every function of degree, whatever degree it is, that's how many x-intercepts it can have, up to. So this is a degree 3 function. It can have up to 3 x-intercepts. It can only cross the x-axis 3 times. It can't cross it more if it's a degree 3. It can cross it less, so it might not have 3 total x-intercepts. Alright, so these graphs are curves, and so they have turning points where they change from going up to down, increasing to decreasing, or from decreasing to increasing. They would have a turning point. The turning points have names. They're either called maximums or minimums. If it is the highest the graph ever goes anywhere on its entire domain, then that's an absolute maximum. But if it's just a maximum within a certain area, it's called a local maximum or local minimum, and I will talk about that when we get a picture up here. Alright, so for the first equation, of course you can't see it because my thing's in the way. So the first function we're going to do is y equals x cubed minus 27x. So what I would like you to do is put that in your graphing calculator and pause this video and then come back when you've got it. Down here on the bottom of the screen we have the graph of x cubed minus 27x. Part B says find the local max and local min if possible. On this graph they're already labeled, but on your calculator, if after you've adjusted your viewing window and can actually see the entire graph, you would press second trace, which is also second calculate, I say all the time. And if you're looking for a maximum, you push the button that says maximum, and then you go to the left side of this and the right side, enter an extra time at the end, and it should read out these numbers on the bottom of your screen. This is called a local maximum because, as you can see, the graph continues up over here, so it is not absolutely the highest this graph ever goes. It's just the highest in this little localized area. So this is a local max, this is a local min, and we would find that value using the same second calculate the minimum. But part 3, where is the absolute value maximum of this function on the interval from 0 to 3? Well, on the interval from 0 to 3, we want to look at it only from 0 to 3. I kind of missed on there. So only looking at the graph in this interval right here, what is the highest that it goes? Well, the maximum in this area is 0 because it looks like this graph goes through 0, 0. So the the absolute max in this interval is 0. Next question is a data table. So we have this table of data representing the number of millions of elderly in the workforce for the years from 1970 and projected to the year 2050. Notice that this equation function that they gave us is where x is the number of years after 1960. So that's going to be important when we're putting this in our calculator. So get your calculators out. We're going to put this data in. To put our data in, we push stat, edit, and then we start putting numbers in. Now we don't want to put in 1970 because x represents the number of years after 1960. So instead we're going to start with 10, 20, 30, 40, 50, 60, 70, 80, and 90, and put those in your L1 column, and in L2 you're going to put these data values. Alright, once you get those in, unpause the video and we will continue. The questions for this problem are asking us to graph the data points and the function on the same axes using this window. So first of all, we have our data in our calculator. How do we get it to show up on the graph? We have to turn the scatter plot on. So to turn it on, you go to second y equals, where it says stat plot on your calculator, and make sure it's on. Next thing you need to do is make sure that your window is going to work for that data. They gave us a window here, so this is your x min is 0, your x max is 100, your y min is 0, and your y max is 12. You can change the scale if you choose to. Alright, that will get your data points on there, and then in order to get the function on the same graph, we would go to y equals. Go to y equals and put this function right here in y1, and you're going to have to type all those numbers in, and then press graph and see if you see the curve and the data points together. It should look like this. Here's a picture of that answer. Okay, part B, the question is, use the model to predict the number of elderly workers in the year 2025. Well, if you recall, this data started in 1960, and we're talking about the year 2025. So we want to know 65 years later, how much is this worth? So you have two ways to do this. One is we have the equation, so we could just plug a 65 in here, but that would require retyping the entire thing. So instead of doing that, since you already have it graphed, when you're looking at your graph, you can calculate the value. So you go to second trace, which is the calculate button, and go to number 1, the value, and it should say x equals, and you get to type 65, and then it will spit out the answer to you. So the y value is 8.68 when you do that. What does that tell me? It tells me 65 years later, which is in the year 2025, there are 8.68 million elderly workers in the workforce. Part C is asking us to find the year in the period from 1960 to 2060 in which the number of elderly workers is expected to reach its maximum. Keyword there, we are looking for the max. So take a look at this graph. It said over these entire years. So we're looking for the maximum. We're going to use that second calculate maximum button and find that value. When you do that, you get x equals 83.77 and y equals 10.27. We'll go ahead and round that to the nearest year, so that's 84 plus the 1960. We got to start at 1960 always. So that ends us in the year 2044. There will be 10.3 million elderly workers, and that is the maximum predicted on this time frame. That concludes, part D, sorry. Part D just asked us on a certain interval what is happening. So on the interval, after its minimum happens at 20.5. On the interval starting at 20.5 and going to 83.8, what is going on here? So when we look at that, the minimum, it's telling us the minimum is 20.5, and we already found the maximum is at 83.8. So what's happening to the graph in here? All they're asking for is that it's increasing. So because that was from the minimum to the maximum, it's always increasing in that interval. It's never changing direction. That concludes part 1 of lesson 6.1. See you for part 2.